So the process I described earlier at length in the last video for binary search, it has to have a sorted data. It has to have a sorted thing to look over. Now, the numbers don't need to be like in strictly increasing, like in a, they don't have to be adjacent to each other. So for instance, I could do 1, 2, and then 14, and then, as long as they are sorted though, binary search will work. So that is just one thing to realize about this. But essentially what binary search will do is that we'll take that, we'll do that whole game that we were playing earlier. Take the middle point and then say, hey, is this the item I'm looking for? And then I'll be able to look at whatever at that point and see if I need to go lower or higher. Okay? So that's pretty much what binary search will do. So let's go ahead and I will actually cut out some of these numbers so that we can look. Yeah, it's not the most glamorous thing here, but let's get it down to a power of 2, right? So what we're going to do is that we've got 32 numbers here. So let's go ahead and search for the middle number, right? The middle number in here will be the one that basically, how many numbers is this? We've got, if we grab 16, then basically we'll have how many on each side? We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if we grab 16, we'll have 16 on this side. And if we grab, and then we have 16 over here. So grabbing 16 seems a good idea. So let's say we're looking for the number to see if the number 23 is in the array. What we'll do, what that would take is that if we were searching linearly, that would take 7 steps to get there. But if we use binary search, what we'll do is that we'll say, hey, are we looking for 23? Yes, we are. So what's in the middle? 49 is in the middle. Okay. 23 is less than 49, so it's obviously in this subsection of the array. So now we look in the middle of this, 1 to 15. So let's go over here to 7. Or, sorry, let's see, 15. So 1, 2, 3, 4, 5, 6, 7. Right, we would want to look at 8. Because we'd have 7 on this side and then 7 on this side. I'm looking for 23. And 8 and whatever is an index 8 will say, nope, sorry, I'm 24. That's so you'll want to look to this way because that's where 23 will be. Okay, so 2 steps. So now we look at 4. And we go, oh, 23 is higher. Then we're at 22. We say 22 is higher. And then 23. That took less than 7 steps. So this is much quicker, even if the thing is very much at the front of the array. Because we have 32 items, right, this will be guaranteed to take, since we're splitting it in half, 5 steps, if we do it correctly. So hopefully that past one took 5 steps, but it really is a very short algorithm. So let's go ahead and take a look. 5, yes. So let's take a look at how to code it. So let's go ahead and write binary search. Public static int search. And now we're going to search an integer array for a target. And we're going to do this again recursively. We are going to just simply return a private method, which will be search. We want to search int. We want to search the array. And we're going to search for the target. And we want to search in between these bounds. 0 and r.length minus 1. Those are valid indices. So let's go ahead and write the private helper method for this. Private static int search. Well, recursive or helper method, but r int target. Got ahead of myself there. Int start. Int end. Right, these are the valid bounds of the array. So we need a terminating condition If let's see, if start is greater than end, right? In other words, if there's no actual space left, right? If there's nothing to look for, then return -1. So the first thing we need to do is that if we're working within the bounds of start and end, we need to find out where the middle item is, what the middle index is. So int middle is equal to, and you might be thinking, how do we do this? Right? How would I figure out what the middle is for, say, oh, I've already closed code, but whatever. How would I figure out what the middle number is in, say, so I've got how many? 1, 2, 3, 4, 5, 6. Yeah. Let's just go ahead and do, yeah. So how do I figure out what the middle index is here? I've got 10 items. Well, let's go ahead and, it's not even. So let's go ahead and just make it even for the sake of making it easier. So now we've got 11 items. Or sorry, odd for this. We've got an odd number of items now. So now if we choose if we choose the item in the middle, we'll have the exact same split. So we'll want to choose index 5. We notice that basically 5 happens to be the 11 divided by 2, right? In terms of integers. So the middle index is the end index divided by 2 over here, or at least the length of the array. That's actually pretty useful. On the other hand, though, say, though, that we needed to do, and let's increase, let's go over here again. Say we needed to search just this subsection of the array and grab the middle and find the middle element. So from 4 to 8, indices 4 to 8. How would I find that the middle element is 6? Well, if we notice something about 4 and 8, if we add them together, then we would get 12. 12 divided by 2 would be 6. So let's go ahead and test it out. Wait, what about, say I wanted the middle of 2 to 8? That's 5. 2 plus 8 is 10. Divided by 2 is 5. So we've kind of got an equation that we can use over here. We can use start plus end over 2 is equal to the middle. Only don't do what I just did there, because actually that's totally a bad move, because order of operations, that would have been end divided by 2 plus start. So here we want to do, so the middle index is equal to start plus end divided by 2. That will give us the middle element, the middle index, right? So int item is equal to, let's go ahead and retrieve it. Actually, we have no need to retrieve it. We can just simply ask now and look for our next base case. If array middle equals target. So if the thing in the middle is what we're looking for, congratulations, we found what we're looking for. So return that index. Great. Shot in the dark, bam, we got it. Otherwise, we need to look lower or we need to look higher. Right? So otherwise, we'll ask if array middle is, or if target, rather, if what we're looking for is less than the thing we're looking at, then we need to look to the left side, right? Right? If we're looking for something at index 5 and we see, so if we're looking over here and we say, hey, I'm looking for 2, we need to look to the left of 6. So we need to look to the left. So we'll return, well, we just need to return the same function. So what do we need to return? Search. And what am I searching? I'm searching target for, I'm searching array for target. So all that's changing is the range. My start should be the same, right? Because that doesn't change, right? Right? If I'm searching this whole thing first, and I choose this is my starting point and say, hey, I'm looking for all the items that are, rather, this is my starting point, and I'm looking for something that's less than this, then the starting point really hasn't changed at all. So what has changed is over here, this used to be the last index. Now this is the last index. Otherwise, if I'm looking to the right, it's very similar. Array target, I'm going to search starting at middle plus 1, so 1 to the right, and go up to the end of the end. And that is binary search. So let's go ahead and say, let's go ahead and generate, like, I don't know, a random array of, int, new int. So let's say we've got 1,000,000 items to search for. For I is equal to 0, I is less than array.length. Sout. Yeah, sout. Not sout. Here, what we need to do is that we're going to test this, so we're going to store our item. R of I is equal to I. And then we're going to sout search for the array for, let's say, 15. We run this, and searching that takes basically no time whatsoever. If we were to do, say, our linear search over here, let's go ahead and switch it to a, well, that will find it very quickly because that's the beginning. So let's go ahead and switch this to -13. How long will it take to figure out that it's not there? Well, our linear search just goes too deep. It's not able to find it because we get a Stack Overflow. Too many layers of recursion there. Oops. Wouldn't take too long if it was iterative. What about our binary search, though? Okay. Notice that didn't take much time at all. So let's go ahead and do our patented method of slowing things down just so slightly. So each time, now remember, with the linear search, this is always a local decision. So what I have to do is to slow this down, I have to put a for loop over here for I, and let's do 100,000 print line statements or print statements. System.out.print. Okay. And that still goes blazingly fast. Go ahead and back up to 100,000. Going to 1,000,000. It's still going to go really fast. 10 million. Okay, spent, yeah. 100 million. It goes really fast. Let's go ahead and now look for something in it. Let's go for that number. Sure. And it finds it. No worries. It happens to be located at the same index as the value.